Okay, so we all know forests are important. I mean, we're practically counting on them to help us fight climate change. But the real story of how they store carbon, well, it's way more complex and honestly way more fascinating than you might think.
We ask so much of our forests, don't we? But how do they actually do it? Today we're going to dig into the science and move way beyond that simple idea of just planting more trees to really understand the powerful mechanics at play here.
All right, first things first, let's get on the same page. The key term here is carbon sequestration. It's basically nature's process for grabbing CO2 right out of the air and locking it away. And you guessed it, forests are the undisputed champions of this game. So first up, we're going to explore how forests act as these giant carbon sponges for the Earth, and more importantly, how that sponge-like ability changes over a really long time.
Our story starts right here. Researchers were curious about this specific forest, which is sitting right on the edge of a big industrial city. They wanted to know, how has its ability to store carbon changed over decades of growth? To figure this out, they dug into incredibly detailed forest data stretching back half a century. This gave them this amazingly clear picture of the forest's long-term performance. It's almost like watching a time-lapse movie of its carbon-capturing life. And the results? Well, they were just crystal clear. You can see it in this chart, a steady and really dramatic increase. From 1972 all the way to 2002, the total amount of carbon locked away in these trees just kept climbing and climbing. And the sheer scale of this is pretty staggering. Over just 30 years, that forest locked away an extra 64,000 tons of carbon. I mean, to put that into perspective for you, that's like taking more than 14,000 cars off the road for an entire year. Just wow.
So here's the crucial point. As these forests got older, their capacity to store carbon grew a lot. This gives us our first major takeaway. Time and maturity are absolutely critical ingredients for a forest's carbon-storing power.
So we know that maturity matters. But, this naturally leads to a really important question.
Is it really as simple as saying, the older the forest, the better? Is age the whole story? I mean, is it just a matter of letting any old forest grow for a long time? To find out, we're going to travel to the boreal forests of northern Mongolia. You know, those huge, cold climate forests? A totally different study here helps us answer this by looking not just at the age of the forest, but at the specific trees themselves.
And it turns out a huge piece of the puzzle is hidden right under our feet in the soil.
So what the researchers did was compare the soil under 4 dominant tree species. You've got 3 types of conifers, larch, and 2 kinds of pine, and then 1 broadleaf species, the silver birch. They wanted to see if the type of tree actually made a difference.
And let me tell you, the results were pretty surprising. It proves a really fundamental rule. When it comes to storing carbon, not all trees are created equal, not by a long shot. So here was the big surprise. The broadleaf birch stored way more carbon in the soil than all 3 of the coniferous species. It was the clear winner, while the Scots pine, you can see, stored the least.
Okay, so what is the secret here? Why would a broadleaf tree, like a birch, outperform those classic hardy conifers when it comes to enriching the soil? Well, it all comes down to their leaves. Think about it. Pine needles are tough, right? They decompose super slowly, and they build up this thick mat of organic stuff on top of the ground. But birch leaves, they break down fast, mixing all that good carbon deep into the mineral soil itself.
And of course, it's never just about one single thing. It's always more complicated. These kinds of analyses show that carbon storage is this delicate dance between the tree species, the local climate, the slope of the land, even the geography. Where and how that carbon gets stored depends on a whole bunch of forces all working together. So, after this incredible journey into the hidden life of forest carbon, what's the big takeaway?
Look, the crucial point is this. Designing our future forests is a sophisticated science. It is not just about planting trees, period. It's about understanding that older forests can be way more powerful. It's knowing that sometimes a birch might be better than a pine for soil health. And it's remembering that what's happening underground is a massive, critical part of the whole equation.
So that leaves us with this final, really critical question. Knowing that tree type and age and the soil all play these super intricate roles, how do we actually go about designing the smarter, more resilient, and more effective forests that we so desperately need for the future?